Hello and welcome. In this video I'm going to simulate the compressor stage of the stage of a compressor in a jet engine for my control project, specifically FADEC. So quickly here, I have an if statement that checks if the engine is running. So if it's running, it runs this code. This is Octave, by the way. It runs this code. This is the compressor inlet function, which takes in these parameters, the RPM, the total temperature, the inlet, and all that. And it returns the mass flow rate and the axial velocity. That's the compressor inlet. Then afterwards, it will pass the mass flow rate and the axial velocity to the compressor function, which will this will be passed along with the RPM and the total pressure, the inlet, for all those calculations. After the calculation, it should return the power required by the compressor, the mass flow rate flowing through the annulus, then the total temperature coming out of the compressor. So quickly we can go to the compressor and see how I've implemented it. Here is the compressor. So as I shown you earlier, these are the parameters that are coming in, and you have our annulus dimensions here. So in this compressor function, it has several stages, which is a stage is a rotor and a stator. So in each state, the air is getting compressed. There's diffusion, and the air is getting compressed, and the pressure and the temperature increases. So we need to calculate how it increases and how safe the compressor stage is from stalling. So I have my constants here. I have the lambda, this is my efficiency, then the specific heat ratio, and then the RPM. This is the formula. I get the circumference of the radius at the middle makes while it turns, and multiply it by the rotations per minute. Now per second, I mean in seconds. So this will give me the speed of the blade speed. Then we have our while component. So for a 2D model, the thermodynamics cannot be captured as accurately as you would when you are using a 3D model. So because of that, I have a predefined values for the Dehala value, which is which is got by iterations, and in every iteration you get a new psi value, which is a new loading coefficient. And with this you can get the change in the while in the velocity diagram, and this shows us the loading that we have. It will in turn affect the Dehala value that we get. So if it's stalling, because our 2D model isn't capturing everything, I'm manually correcting it to a value that is acceptable for the compressor. So this is my first stage calculations. So I'm returning whether it's stable. So I'm checking the Dehala value and checking if it's above the Dehala stall value that I placed, and if it's above, it's stable, will be true, that is returned as true. And the power required by the compressor is the mass flow rate by the speed of the blade, and by the difference of the while, the C2 the CW2 minus the CW1. And with this, I return it to the main. Let me just make this bigger. Oops. Yeah. I return it here. I return it here, the power required by the compressor. So this will be the sum of all the stages. This is the first step of me designing it. Let's test it and see how it works. Let me start up my engine. I just call the made file and it will start up. It's waiting for the client connection. Here is the complete model of my simulation at the whole system. So at the top here you can see this is the engine model. I'm building it using Octave, so it's built from the basic thermodynamic and mathematical formulas and functions. So that's what's calculating our thrusts, calculating our loading at the compressor and all that. And then it's connected to our ECU, which represents the ECU that's on the side of the engine, the side of the real engine, that is. The work of the ECU is to control the settings of the engine so that it delivers the thrusts that it's set to. So it's pulling to a thrust that it's set to safely, and all that's entailed in that. So I'm handling this using Spring Boot. And then the ECAM and the front end, I'm using Flutter just to see what's happening on the engine. I'm returning the data all the way back. So I'm using WebSocket to communicate from the ECAM to the ECU. Then from the ECU to the engine, I'm using the TCP, the raw TCP protocol, where I'm sending bytes and unpacking them, reading and sending back bytes, data in bytes. So that's the setup. Let's go ahead and test now. So to test it, I'll just click on view ECAM here and then connect to our engine. So you'll see that it's connected and it's connected. That's via the ECU at the back end. Then start engine. You can see that the values are running, but it's like it's oscillating between stall risk and converging to the correct value. And then you can see the N1 here has pulled to 22%, and the bleed pressure is constant at this point, and the bleed air temperature is constant at this point. Yeah, that's what I'm seeing. It's spinning the N1 because I designed a single shaft engine, so that's why you're seeing the N1 being spooled by the APU. But if it were double spooled, or if it had two spools, you'll see the N2 being spooled up.